All right, hello everyone. So today we're going to be doing our last R tutorial. So this tutorial is going to be about binary dependent variable models. So that is probit models, logit models, as well as the linear probability model, which we've been kind of doing up until now without really kind of having a specific name for it. So let's get right into it. We'll load up the lecture 9 demo data. So you can find wherever you stored that. And grab that snippet of code, create our new R scripts, all the usual good stuff. So we won't be needing the AER package today. We're not doing anything with instruments. So instrumental variables you can do with a linear probability model, like we covered in class. You can't really do it with the probit or the logit. So since we're going to be doing some probit and logit stuff today, we're not going to be using the AER package. Fortunately, we don't need any new packages for doing probit and logit. It's part of base R. Okay, so let's make sure we're grabbing that data. Doing our usual filter, make sure that we're not keeping any rows of data that might have missing observations that could mess with our analysis. All good there. So let's start things off. We'll start it off with the linear probability model. So let's take a look at our data and see what we're working with. Okay, so it's just kind of a Y, an X1, an X2, and an X3. So nothing too interesting here in terms of interpretation, just some kind of generated data. Looks like we have continuous variable for X1, continuous variable for X2. It seems like the variable for X2 only takes positive values. And then we have a Bernoulli variable for X3. So we can go right ahead and just do our linear probability model. And to run that, we just use our usual LM command, our linear model. And we include all of our regressors. Okay, so this is identical to a multiple regression. There's nothing different here. We're just calling it a linear probability model because Y is Bernoulli. And because Y is Bernoulli, we kind of predict the probability of the Y equaling 1 for any given observation, and we interpret the coefficients of our X variables as being the marginal change in the probability that Y equals 1 when that X variable increases. So very good. So we can run that pretty easily. Whatever it happens to be, let's make sure we're recovering the robust standard error. We're going to want to compare all of our different models together in a table. Okay, so that's our linear probability model. And then we have our probit and logit models. So for probit, what we have, let's call this probit 0, is this command GLM. So GLM stands for generalized linear model. So linear model in the sense that what's inside the probit is still a linear function of the parameters, beta 0, beta 1, beta 2. Generalized in the sense that we allow kind of an external function to modify what's inside and kind of create a nonlinear effect on Y. The notation is exactly the same. We still have this kind of formula notation in R, where we have our left-hand side variable Y, tilde, X1, X2, X3, our right-hand side variables. We're still reading in our data, DAT. The only thing that's different is we have this additional specification, family equals binomial, and then it's recommending us, oh, link equals logit. We could do that, or we could do link equals probit, which is what we're running here. So let's start running our code, make sure there's no errors. All right, all good there. And then, yeah, like our command was suggesting, we want to run a logit model. All we need to do is use the link equals logit. Easy. Okay, so we'll make sure that we're recovering our robust standard errors. Double check that. That's going to work correctly. Indeed. Our logit standard errors. And so finally, we can kind of put all these things together. What's interesting about the differences between these three models. Okay, so we'll take a look. What we can see is that when we look across these different coefficients, one thing you'll notice is that they'll always be the same sign typically. The constant doesn't really count, but the marginal effects of each variable, x on y, the sign of that is always given by the sign of the coefficient. For OLS, that's also the magnitude of the percent of the probability change in y from a 1 unit increase in x. For y, or for probit and logit, this is no longer the marginal increase in the probability of y equals 1, given a 1 unit increase in x. But the sign of it does still tell us that if x2 goes up by 1, the probability that y equals 1 will increase. Okay, so the sign is still informative in probit and logit about the direction of the effect, but the magnitude is no longer informative about the size of the effect in terms of its marginal effect on predicted probability. And like I said, the signs will typically agree between all three models, almost always. Okay. We can see that the significances are also basically the same. Which coefficients are significant are the same across the linear probability model and the probit and the logit. Okay. Awesome. So one thing that we discussed in class that probit and logit are good for, that linear probability is not so good for, is visualizing predicted probabilities and making sure that those predicted probabilities are actually probabilities, right? That they stay between 0 and 1. So how do we visualize these predicted probabilities? Well, with the regressions we've run right now, we can't really do it that well, just because we've done these as multiple regressions. So we can't really visualize this on a graph of kind of like an X against a predicted probability, just because we have multiple X's. So one thing that we could do, and we'll go back to the single variable case, but one thing we could do for now is just look at the predicted probabilities in kind of like a density plot or a histogram plot. All right, so let's do that now. So to predict probabilities, we're going to add another variable to our data set, which is the model's prediction of what the probability of y equals 1 is for each observation. Okay, so for the linear probability model, we'll have, say, y hat for the linear probability model is equal to predict LPM. So we use this predict command. Run that. And then if we take a look at DAT, we can see that here's our predicted y hat. So this is the predicted probability that y would equal 1 for that observation. So for an observation with these x values, this is the predicted y hat. Okay. What about for the probit and the logit? It's similar. But for probit, we're still using the predict command, but we need to make sure that we include type equals response. Otherwise, it will just predict what's inside the kind of probit function. It'll multiply the x's by their coefficients, and then that'll be it. But we want it to multiply the x's for that observation by their coefficients, add them up, and then apply the probit function to it so that we get that number between 0 and 1. That's what we'll do. Same thing for logit. Okay. So now we can kind of take a look at each of these different variables on a density plot. So let's look at like what are predicted probabilities for the density of our predicted probabilities for each of these different models. And the idea here is we're going to look and see, okay, are these models predicting numbers between 0 and 1, or are some of these predicted probabilities less than 0 or bigger than 1? Right, so we'll do ggplot DAT. And we'll have a point on here, which takes the aesthetic where x is equal to y hat LPM. Say the color of this can be red. Actually, let's not do geom point. We'll do geom density, right? Because we want to do kind of a histogram style thing, but for a continuous variable. And then we'll do more densities on the same graph for these different predicted probabilities from the different models. Okay, so let's see what we get with this. All right, so what we can see here is that our red, which is the linear probability model, it's got kind of like a higher peak around the middle, so it's predicting more things around a probability of 0.5. And then we see that it also has fatter tails, so it's predicting more things above 1 and below 0. Now you might be thinking, well, hold on, why are the density curves, which kind of show the weight of observations at each of these points, why are they bigger than 1 and less than 0 for the models where our predicted probability should always be between 0 and 1? That's a good question. So the reason is when we draw these density plots, the way that R does it is it kind of like smooths all the points nearby, and it kind of takes an average of those points. So even once it gets above 1, it's still kind of taking the average of points that are nearby to create this kind of smooth curve. If we want to get rid of that, I think geom histogram might be the way to go. This is going to look a little ugly, I think. Yeah, quite ugly, actually. Good, but when we look at this kind of this graph, we see, we have the green plotted points that always fall between 0 and 1. We have the blue points, right? So green is logit, blue is probit. So the probit points are always between 0 and 1. Here, it looks like they're above 1 because the bar kind of extends over, but these are all below 1. Whereas with the linear probability model, the red, we do see that some predicted probabilities are below 0, and there's a bunch that are above 1, right? So a little bit of an ugly graph, but we can see here that, yeah, the kind of probit and logit are predicting the probabilities between 0 and 1 that we expect, while the LPM is predicting probabilities bigger than 1. So one other way that you could visualize this is you could plot the LPM points against, say, the probit points. All right, so what are we doing here? At this point, what we're trying to do is visualize the quality of our predictions, right, from these 3 different models. So we have these 3 models. We recovered some coefficients, and we're trying to see, okay, which ones are best behaved in terms of how they're predicting the probabilities, right? So here we have this curve, which is the predicted probability for any given observation in the data set. You know, for say this observation, the LPM predicts it to have a probability of about 0.4. The probit model also predicts it to have a probability, here it looks like 0.375 or so, right? What we can see is that the LPM, there's numbers above 1 here, right? There's numbers above 1, which means that, you know, the LPM is predicting these observations here to have a probability greater than 1. Whereas the probit, you know, 1 is up here. So we're always predicting these observations to have a probability less than 1, right? So you can see kind of through the middle of this plot, the LPM and the probit, they kind of agree. But as you get towards the more extreme observations, the probit starts to sort of curve them so that they stay below 1. And the LPM would predict that they're above 1, right? Perfect. So that's kind of 2 visualizations there. And this is also how to kind of predict. Now, these predictions are all at given observations in the data. When you feed a model into this predict function, it's going to assume that you want to predict at the data points that were used to fit this particular model, right? And that's why when we use the mutate command, we can automatically just generate a new column, because it's going to predict at each observation the predicted y hat from this model. What if we want to predict at new points, right? Points that aren't in our data set. Well, we can do that. That's totally fine. We just need to create a new data table of points that we want to predict at. So we want to predict probabilities at specific points. And this will be useful for your homework. So let's create this prediction data table. And the command to create a data table with the tidyverse is tibble. So we need to give it all the variables that we have in our data set that were used to fit the model. So we need to give it values for x1, x2, and x3. Let's say, you know, x1 is 2.3 and 1. x2 kind of always seem to be positive. So let's make sure that, you know, we're including only positive values. And then x3 was Bernoulli, so we can just do some Bernoulli values. So these are just random arbitrary values. I just picked them as an example set of values. In the homework, you're kind of asked to predict probabilities at a specific set of values. So you'll need to supply those values, right? And now we can predict, say, the logit. Again, wanting to get those responses, and our data that we're predicting at, we'll need to assign with this new data argument, and we want to give it the prediction data table. So we run this and we end up getting 2 numbers. So what are these numbers? Well, when I look at this data table, pred dt, I have 2 observations, right? x1, I filled it with 2 values. x2, I filled it with 2 values. x3, I also filled it with 2 values. Those values correspond to the rows in each of these different columns, right? So what I've done is I've predicted the probability at these 2 observations, right? Where again, the first entry in each of these is the first row in this new little data table. So that's our first observation. The second entry is the second row, right? And then this is our predicted probability for that new observation. Okay, perfect. So good. The last thing I mentioned I would do is kind of the other way to visualize predicted probabilities if we only have one X variable that we're regressing on. So predicted probabilities with one X. So let's do a simple set of models here. We have our linear probability model 1. So we'll just do y on x1. We have our probit 1. It'll be y on x1. And then our logit model. Run all those. And then we'll predict. So y hat LPM1. Probit 1. Logit 1. Right, so we're kind of predicting these y hats using this new simple model, right? And why are we doing this? Well, I want to show you guys kind of what the predicted probabilities for these different models look like compared to each other. And it's easy to visualize that when you only have one X variable. Right, so these all look good, right? Run. And now we can do our plot. We'll do g on point, x equals x1, and y equals y hat LPM1. This color can be red. And we'll have blue for the probit and green for the logit. And then lastly, what we can do is also include the points for the raw data, right? Just see how those would look. Make those black. Missing the bracket there. All right, so that should be all good. Let's run that. Oh, what did I forget to do? I forgot in these prediction for the probit and the logit to do response. So I ended up getting these weird linear things. So rerun that, rerun this. Here we go. All right. So here we have our raw data, which is the black data. And what we can see is that, of course, y only takes values of 0 and 1. So when we look at that y-axis, all the y values cluster at 1 and at 0. X1 takes continuous values. And we can see that, you know, the fact that as x gets higher, it is more likely that y equals 1, which is reflected in our LPM coefficient for x1. All right, so the red is the LPM, and that's our predicted probability of y equal 1 for each value of x1. And you can see it's a straight line like we would expect. As you increase x by 1 unit, the predicted probability always goes up by a constant amount. Even as you breach kind of the barrier of the probability equaling 1, it's still predicting that additional marginal increment. You can see that the probit and the logit, the blue and the green, are very, very similar to each other in their predicted probabilities. And they're somewhat similar to the LPM around the middle of the x values. But then as you get towards more extreme x values, they start to curve so that they never get above 1 and never get below 0, right? So those are our kind of predicted probabilities from the probit and the logit. Now in the homework, I think I ask you to regress, a Bernoulli on age and then age squared. Now, even though you have two variables, age and age squared, they're both functions of age. So if you wanted to, you could plot your predicted probabilities with just age on the x-axis and then the predicted probabilities on the y-axis. I don't think I ask you to, no, I don't. But if you want to, feel free to kind of plot that and take a look. And, if you are doing a project with a Bernoulli response variable, you can definitely make a plot like this if your main x variable is continuous. If your main x variable is also Bernoulli or it's discrete, you'd be better off doing a histogram or a bar plot. Great, so that's it for this week, and that's it for the R tutorials. So yeah, the only kind of extra content now is going to be machine learning, which I'll provide some R coding practice for, but that won't be testable on the exam. So, depending on your time constraints and your interests, you can choose whether or not, you want to kind of get into that. And I'm always happy to talk about that during office hours and during the tutorial. So yeah, that's it. So I'll see you guys in class.